finding equilibrium concentrations. Being able to calculate equilibrium concentrations of reactants and products from a known equilibrium constant is useful in lots of different situations. And so what we're going to do is we're going to see two types of problems. The first type, they'll give you the rate constant. That's the equilibrium constant, and all but one of the equilibrium concentrations. And so then we just plug the known values into the equilibrium constant expression, and we solve for the unknown. That actually doesn't happen very often. The second condition is that we have the initial concentration of the substances, and we know what K is. And so then we can calculate the equilibrium concentrations, and that's going to be using an ice table. An ice table. Ice, baby. An ice table. Okay. So this is the first one where K and all but one equilibrium concentration are known. Diatomic iodine decomposes at high temperature to form iodine atoms according to this reaction. In an equilibrium mixture, the concentration of I2 is 0.1 molar. What's the equilibrium concentration of I? So we write the equilibrium constant expression, and that's going to be I squared over I2. And we know what K is, and we know what I2 is, and so there's only one variable. So Kc is 0.011. We don't know what I squared is, but we do know what I2 is, 0.10. So if I multiply both sides by I did that wrong, 0.1, I'm going to get 0.0011 is equal to the concentration of iodine squared. And so I need to take the square root of that to find the iodine concentration. Any questions? Okay, finding equilibrium concentrations. For this reaction, we've got A going to form 2B, and we're told that Kc is equal to 4. We've got an equilibrium, a reaction mixture at equilibrium that has A equal 1. What's the concentration of B in the reaction mixture? So we don't really need to calculate, but we need to think about this. K is equal to 4, which is equal to the concentration of B squared over the concentration of A. And we're told that A is 1, right? So then 4 is equal to B squared, and B must be 2. Any questions? Okay, this is the more common type of calculation. We've got initial concentrations or pressures, and we know what the equilibrium constant is, but we have no information about concentrations at equilibrium. So this requires a set of steps. First, we're going to set up an ice table with the initial concentrations. We're going to represent changes in concentration in terms of X, and we'll take the stoichiometry into account. And then we'll add the initial and the change rows, the I and the C rows, to get the E row, the equilibrium. And then we'll plug those expressions into the equilibrium constant expression and solve for X. So looking at this example where A is in equilibrium with 2B, we're told that K is equal to 0.33 and A is initially 1. So the reactant concentration is 1. If they don't tell us what the product concentration is, we assume that it's 0. And so that's our initial row, ICE, ice. The change row, the reactant is going to go down in concentration. And we're calling the change X, and we're going to multiply X by the coefficient. So this is just going to be negative X. And the concentration of B is going to increase by 2X. Because for every A that disappears, we're going to form 2 B's. Right? So we know we started with 1 molar of A and we lost X. So at equilibrium then, the concentration of A is equal to 1 minus X. B started at 0, it gained 2X, and therefore at equilibrium its concentration is 2X. We need to find out what X is. Well, we can write the equilibrium constant expression for this. K was 0.33, and that's equal to the concentration of B squared over the concentration of A. We can describe the concentrations of A and B in terms of X, so we're going to substitute those into this equation. So B is 2X, and the concentration of B has to be squared. And the concentration of A in the denominator is 1.0 minus X. So that looks like fun, doesn't it? So, I mean, you can go through the whole math thing where you've got 0.33 times 1.0 minus X is equal to 4X squared. And you can see you're going to end up with a quadratic equation. And there's an equation you can use to solve the quadratic equation. But we're beyond that. Your calculator, most of your calculators, can solve this problem for us. Okay? So if you have a TI-36X Pro, pull it out. We're going to learn how to use it. If you have like a TI-84 or something, I think it can also do it, but I don't know how to tell you how to do it. So I'm sorry.
I have 2 different calculators.
We're not going to talk about Casio.
Okay.
I have 2 calculators and neither is ever the one you need.
Oh. I'm going to pause this here. So when we solve a quadratic, we can often find a positive and a negative root. Only one of those can be the correct answer. So in this example, we're starting with reactant only and no product. Is it possible for the reaction to proceed in the reverse direction? Is it possible to have less than 0 B? No. We can't go in the reverse direction because there's no B to react. So we've got the way this set up this way. The concentration of A is going to decrease by X. X must be a positive number in this example. Okay? Another clue about that is down here, the concentration of B is 2X, and if X was negative, then we'd have a negative concentration, which is not possible.
Yet. Not possible yet.
You're really gonna regret showing us that video.
Yeah. Okay, consider this reaction. Nitrogen and oxygen forming no! So we're starting out with only product, no reactants, and it's saying find the equilibrium concentrations of all three things. So we're given the equilibrium constant, we know the starting concentrations. So I'm going to rewrite this equation down here, the chemical equation, and this is going to be my ice table. So the initial concentration of no is 0.0100 molar. There are no reactants. The concentration of those is 0. It's a bad 0. So which direction is this reaction going to go in? Is it going to go in the reverse or forward?
Reverse.
It has to go in the reverse. There's nothing to react, right? So it has to go in the reverse direction, meaning that the concentration of this product is going to decrease. Yeah? So it's going to decrease, and we're using X as our unknown, and we should use this coefficient of 2. It's going to decrease by 2x, and then how is n going to increase? By 1x, and oxygen by 1x. So your changes, you're going to use x and whatever coefficient is in front of that chemical species. And then to find the equilibrium, we're going to add them up, the I and the C rows. And those are the equilibrium concentrations. We take our equilibrium constant expression, which is no squared over the concentrations of N2 times O2. And that's equal to 0.055. So this is the concentration of NO at equilibrium. So that's what goes inside the little box. 0.0100 minus 2x. And that quantity is squared. And we're dividing by x and x. And that equals 0.055. So doing this on my calculator, I'm getting 0.004475 molar. We could tell if that was correct by plugging it into the equation. It's not negative, so that's encouraging. Did anybody else get that number? Yeah. Yay!
Cassie did
Awesome.
it. How? Tell me how.
Google. There's a little button down here. I'm glad somebody saw that.
So do you have to put something for X?
Okay.
So it is the 0.004?
Yeah. So this is the correct answer. I was looking at it but not thinking very clearly. Thank you, Abel. So if we put this answer in, 0.0100 minus 2 times that gives us a negative concentration. Point 0.01 minus 2 times 0.00566. That tells me the concentration of the product at equilibrium is negative 0.00132, which is not possible. I was looking at this and saying to myself, this isn't bigger than that, what's the problem? But I forgot about the 2. Okay, let's try a different one. Here we're starting with just the reactant and no product. N2O4 in equilibrium with 2NO2. Initially we have 0.0250 and 0. What's the change for the reactant? What should I write in here? Negative X? And then what goes over here? Plus 2X. And, draw a line down the middle if it helps. So this is decreasing by some unknown quantity X. For every 1 mole of this that disappears, we get 2 moles of that being formed. And so this goes up by 2X, this goes down by X. And this time it's 0.36. And that's equal to the NO2 concentration, which is 2X squared, divided by the reactant concentration. And again, we get another quadratic. You can actually use this technique to solve all kinds of equations, even those ones from chapter 15. So mine is telling me that X is equal to 0.02038. And then we have to make sure that that is legitimate. If we put this value in here, I just realized I wasn't actually finishing the previous problem. My bad. I just found X. It wanted actual concentrations. So 0.025 minus 0.0204. So this is going to be 0.0046 molar. And this one's going to be 2 times 0.0204, which should be 0.0408 molar. There can only be one number that actually fits. There's another root, but if you get the other root, you're going to end up with a negative concentration. Any questions? Here's one with pressure. Initially contains both reactants, each with a partial pressure of 0.1 atmosphere, and no product. Find the equilibrium pressures of all three substances. And we're given Kp. So we've got I2 and Cl2 going to 2ICl in our ICE table. Initial pressure of both reactants is 0.150 and 0.150, and there's no product. So what do I put in here for the change for these guys? That change will be negative X, because the reactant concentration is going to go down, and the concentration for the product plus 2X. So we've got 0.150 minus X and 0.150 minus X and 2X. So here Kp is equal to the pressure of ICl squared over the pressure of I2 times the pressure of Cl2. So 81.9 is equal to the quantity 2x squared divided by 0.150 minus x, the quantity squared. X equals 0.12285. So then these pressures are 0.150 minus 0.123. Which is 0.027. And this one's 2 times that. Or 0.246. So that's the pressure in atmospheres of the product. And this is the pressure in atmospheres of the two reactants at equilibrium. That's supposed to be an arrow. It's not a very good arrow either. Any questions?
Where did you get the 0.123?
The 0.123, I rounded this to the same number of sig figs as this. I'm just being lazy. Any other questions? So that was kind of a pain in the butt, wasn't it? Even using the solver is like, ugh. Sometimes we can make approximations that simplify things. This is going to happen actually quite a bit. So if the equilibrium constant is small, that means that the reaction doesn't proceed in the forward direction very far. if our initial reactant concentration is large, then we can assume that X is small. And subtracting a small number from a large number may not substantially change it, right? So, let's say you're hauling oranges and you stop at the truck scale, to weigh your load, and you've got full thing of oranges, and you weigh it. And as you're pulling out, one of the oranges falls off. Does the mass of that orange matter in comparison to the mass of the whole truck full of oranges? It doesn't. Nobody's going to know the difference. You just keep going. That's the idea here. If X is small enough, we can ignore it when it is added or subtracted to something. Of course, we need to check this assumption. And so what we want to do is we want to compare the value of X that we end up with. We have to compare it to the number that it got subtracted from. It needs to be 5% or less to be valid. So how does this work? So here we've got initial concentration of reactant of 1, concentration of product of 0. We've got our changes and our equilibrium concentrations. So 3.3 times 10 to the negative 5, that's a small number. So that's going to be 2x, the quantity squared, divided by 1.0 minus x. In terms of concentrations, 1 molar is pretty large. So we're going to use the x is small approximation. We're going to say x is small, and so subtracting it from 1 is not going to really make a difference. So this number only has 2 significant figures. It's estimated in the first decimal place. If this number is 0.0005, and you subtract and keep your sig figs, it's going to disappear anyway. So then what we can say is, well, here that's approximately 0. You get rid of the x's when they're added or subtracted. We don't want to get rid of this x, because then we've gotten rid of all the x's and we can't find out what x is. So doing that, we get 3.3 times 10 to the minus 5 is equal to 4x squared divided by 1. And so now this is much easier to solve. I got my 3.3 times 10 to the, wrong button, 10 to the minus 5. And I'm going to divide that by 4 and take the square root of it. And I'm going to get x is equal to 0.00287. Solving this simplified equation for x. And x did end up being small. 1 minus 0.00287, if you follow sig fig rules, is still 1. And then the 5% rule is we're going to compare this number to the number it was subtracted from. Is this 5% or smaller of that number? Yes, it is. It's 0.287%. So the equilibrium concentrations then, concentration of A is 1 molar, and the concentration of B is 2 times X. That's not right. 0.0057. Anybody find that disturbing?
Can you explain how you got B?
I got B because B is equal to 2x. So I took this number and multiplied by 2.
Oh, you mean the fact that A appears to have not changed?
Yeah. So our final concentration of A is also 1 molar, and the initial concentration of A was 1 molar.
That is only if we stick to sig.
That's due to limitations in how precisely you can measure that. The amount of product that formed was extremely small. And so, yeah, that's how it is. Let's do another one. So here we have the decomposition of hydrogen disulfide. Reaction mixture contains these quantities at 800 degrees Celsius. Find the equilibrium concentration of the sulfur gas. 800 Celsius. Yeah, that's pretty toasty. So I'm using my chemical equation as the header for my ice table, and then I'm going to write down the initial concentration. So H2S was 0.100 molar, and H2 was 0.1 molar, and S2 was 0. And then I'm going to say it's going to change by X. Which direction is it going to go? It has to go forward because we're starting out with none of the S. So it can't go backwards. It has to go forwards. So S is going to increase by X. H2 is going to increase by 2X. And what is the H2S going to decrease by? 2x. So then I end up with 0.100 minus 2x and 0.100 plus 2x and x. So the expression here is H2 squared times S2 divided by H2S squared. It really is a good idea to write this out and then plug numbers into it. So 1.67 times 10 to the minus 7 is equal to my hydrogen concentration, 0.10 plus 2x squared times my S2 concentration divided by the other one, which is 0.100 minus 2x, quantity squared. Our equilibrium constant is small. This reaction is not going to go very far. So we're going to use the x is small. So if we say that x is small, this gets very simple. Because the 2x then is inconsequential there and there. So we have 0.1 squared over 0.1 squared. Those cancel out entirely. And x is equal to 1.67 times 10 to the minus 7 molar, which is the concentration of S2. We should check that. see if this is less than 5% of what we're subtracting it from. And I believe that gives us 1 times 6, 7 times 10 to the minus 6%. Definitely small enough that it doesn't matter. Any questions? ICE tables are very important in this class. It's not just here in this chapter. We're going to use them in a couple more chapters. So we need to get comfortable with them. Yes?
What would you say would be, not the, I guess the limit or the number you would say is like big enough to not use that rule? Like 10.
You mean for K?
Yeah, for K.
Well, yeah, so how small does K need to be for you to be able to use the X is small rule? That depends on what your initial concentrations are. You know, if K is less than 1, you could always try it. But then you need to double check and see, is what I ended up with, is that less than 5% of what I was subtracting it from? If it is, you can use it. If not, you can't. So, questions on exams will often be X is small approximations so that you don't have to do quadratic equations. Any other questions? Well, this looks very similar, doesn't it? Well, it is very similar. So let's make our ICE table really quick here. Here, our initial concentration is 1 times 10 to the minus 4, and these are 0. So what's different about this problem? This initial concentration is significantly smaller. So the changes are going to be the same. And so when we plug these in to our equilibrium constant expression, we are going to have X squared, that's the hydrogen, times X is the sulfur, divided by 1.00 times 10 to the minus 4 minus 2X squared. Well, let's try X is small anyway. If we do X is small, then that part disappears. So then we have 1.67 times 10 to the minus 7 times 1 times 10 to the minus 4 is equal to X cubed. So I'm looking for the cube root of 1.67 times 10 to the minus 7 times 1 times 10 to the minus 4.
For the change, page 2.
Oh, I did that wrong.
Okay,
Thank you. Thank you.
I thought I missed something.
No, no. This change is plus 2x.
Okay.
Yeah. Yup. Okay. So this is 2x squared. So here, we need to divide by 4. I'm getting 6.39 times 10 to the minus 5. Anybody else? Let me try that again. So I need the cube root of this. One 1.67 times 10 to the minus 7 times 1 times 10 to the minus 4 divided by 4. Yeah, I did something wrong the first time. One 1.61 times 10 to the minus 1, 2, 3, 4. Is x small?
Very.
Well, it's small, but is it small compared to what we're subtracting it from?
No.
No. It's actually larger than what we're subtracting it from, which means we can't use this approximation. So then you're back to your number solver. Over 188 minus 4 minus 2x is equal to 1.67 times 10 minus 7. Mm-hmm.
For that one, don't we supposed to multiply by 10 to the negative 8 instead of the 10 negative 4 because you squared it? On the red one?
Here?
Yeah.
Good catch. Thank you. Yep, I screwed that up too. This was down here and it was squared, and so that should have also been squared. I think that's gonna make x even smaller, won't it? So this is 7.47%.
Negative six.
So in this case, we can use the X is small, cause it got small? No.
It looks small, but when we check it, it's actually 7% of what we're subtracting it from.
It's supposed to be 5% and under?
Yeah,
Okay,
yeah,
sorry, distracted.
That's okay.
yeah. Mm-hmm.
Why'd you cross out the 2x in the beginning?
I crossed this 2x out because I was doing the x is small approximation. We're saying x is so small, we're hoping, that when I subtract 2 times it from this number, it doesn't really change it.
Okay, and then you would leave the 2x on top there because.
I need to leave these x's, these are multiplied by things, they're not subtracted or added to things. Yeah. So anywhere that x will be added or subtracted in the x is small approximation, it just goes away. But you have to leave x other places.
So in this case, we need to plug X, what we found X to be, into the table? Or to the equilibrium
Well, so
value?
we can't say that this is x
Oh.
because
Got rid of the 2X.
because it's too big. X isn't small. So we need to use the whole math business.
So we would just use the whole thing and type it into our number.
Number solver. Mm-hmm. And we would expect to see an x that's not crazy different from that.
But hopefully smaller.
Including that 2X.
I'm getting a no sign change error. It's lovely. If you get no sign change error, you either made a mistake or you need to start x at something other than 0. So 6.78 times 10 minus 6. It's very similar. Okay. Okay. We did that one. There we go. So for a generic equation, it's showing me different things on the computer and my iPad, which is a little confusing to me. So here we have a reaction, A goes to B, consider each value of K and initial concentration of A. For which set of values does the X is small approximation most likely apply? So are we looking for large K or small K? Small K. Large starting concentration or small starting concentration? Large starting concentration. So looking at these two are larger Ks, so it's probably one of the first two. And then this is a much larger concentration, so it's got to be A. So notes. Concentrations have to be in moles per liter. If you have partial pressures, they have to be in atmospheres. Use the appropriate equilibrium constant. Kp or Kc, depending on whether you have pressures or concentrations. We don't want to use moles in our ice table instead of concentration. It can be done in certain circumstances, but you have to have the moles of reactants in the chemical equation equal to the moles of products, otherwise it doesn't work, so let's just not do it. We're using concentrations, not moles. And the X is small approximation does not mean that X is 0. It just means that X is very small.